Yeah, good afternoon, everyone, and thanks to the organizer for giving me the opportunity to present our work. I've been working on this project together with Adam Heugil and Gabriele Chiara at um, Queen's University in Belfast. Um, the system I want to consider today is a system composed of n subsystem and baths. And each bath drives a transition of a corresponding subsystem. So in this cartoon, you see, for example, three um, spins in contact with three heat baths at different temperature. And you see that, here we have two states, a transition between two states where only one spin, the spin one, has flipped. This morning, Janet told us about the transition from classical stochastic thermodynamics to quantum thermodynamics. And um, in in stochastic thermodynamics, the local master equation is the standard, where the situation is the one that I depicted in this cartoon, where a single bath drives the transition of single degree of freedom. And in the classical case, you can prove immediately the second law of thermodynamics in the form of the positivity of the entropy production rates. Once you have identified the system entropy and heat current associated with each path, and this inequality follows immediately, from a mathematical point of view, essentially from the concavity of the logarithm function. Things gets a bit more complex when you deal with the quantum local master equation. So the goal that I set for myself today is to fill this red box. So given the entropy production rate, when this quantity is positive, and so I want to know how which quantity I should put into this red box. And this question originates, amongst other reasons, also by a well-known paper from Levy and Konslov. And they prove that with a local master equation, when you consider two quantum harmonic oscillators in contact with two heat baths at different temperature, you can observe that the steady state current flows from in the opposite direction of the temperature gradient. So essentially, you can obtain the result where the heat flows from the cold to the hot reservoir. And well, once I have filled up this red box, so once I have given a definition for the heat current that enters in the second law of thermodynamics, I will apply the result to stuff that work as an absorption refrigerator. Okay, so let me set the stage. I consider here a system with Hamiltonian H in contact with NB bats. Rho is a density matrix for the system, and I've written here explicitly the expression of the dissipator entering the master equation, and set of cats that form an orthogonal basis for the system. And this set of cats might or might not be eigenstates for the Hamiltonian. So the situation that I have in mind is indeed the case where this set of cats are not eigenstates of the Hamiltonian. Then I chose the jump operator to connect the state J with the state J prime. And in my notation, lambda denotes a transition between these two states. The dissipation rates appear in here, satisfy a local detailed balance condition. Beta alpha are the inverse temperature. Well, beta alpha is the inverse temperature of the bath alpha, and omega alpha is the energy difference between state J prime and J. So by J prime and J here, I have in mind the situation depicted in this cartoon, where I flip only so the difference between two states correspond to the difference between only subsystem. Okay, so well, this is a kind of a standard definition for the master equation. Um, and yeah, I introduce here the dual of the dissipators. Um, and now well, since I have chosen an arbitrary set of cats, I can split the Hamiltonian in its diagonal and non-diagonal part, HD and HND. And then I consider the time derivative of the Hamiltonian. Well, since the Hamiltonian commutes with itself, this time derivative is just given by the sum of the dual of the dissipators applied on the Hamiltonian. And then I split the Hamiltonian in the two parts. So I have these two terms on the right-hand side of this equation. And then just a matter of operatorial algebra. Well, I plug H into the dual. I turn the crank, and I'll obtain that these terms takes this expression, and this term takes this expression. Indeed, this term is diagonal in the chosen basis, and this term is non-diagonal in the chosen basis. And then I consider the standard definition of heat current flowing from or into the bath alpha. So Q dot of alpha is just the trace of H times the dissipator alpha applied on the state rho of the system. And again, after some manipulation, I find that this current can be split into two terms. One that arises from the diagonal part of the Hamiltonian, and one that arises from the non-diagonal part of the Hamiltonian. And I call these terms Q dot diagonal and Q dot non-diagonal. Okay, these are my definition. And then, well, the first goal that I set for myself was to prove the second law. And well, the proof goes as follows. I introduced the system entropy as minus trace rho log rho. And then I use the Spohn's inequality that states that for any superoperator X or Lindblad form with a given steady state rho SS, the following inequality holds. So rho of t is the solution of the Lindblad equation at time t, and rho SS, as I said, is the steady state for this operator. And then, well, if you apply this inequality to each of the what we call the thermal equilibrium local states. So you see here you have the inverse temperature of the bath alpha and the diagonal part of the Hamiltonian. You see, again, it's well, after some algebra, you find that the entropy production rate is given by this well, the variation of the system entropy minus this term, and well, the consequence of this inequality is that the entropy production rate is non-negative. So this proves the second law of thermodynamics in terms of the heat currents, but the only heat current that enters the second law of thermodynamics is what I call the diagonal heat current. While this other term doesn't enter in this inequality. Of course, if the Hamiltonian is diagonal in the chosen basis, then this well, the non-diagonal term vanishes. So you're left only with the diagonal part of heat current. Yeah, here I want to make well, some comments and make connection to previous works in this field. So in the previous framework, the expectation value of the time derivative of the Hamiltonian is given by these two terms, the sum of these two terms. In the collisional model framework, the heat current, the non-diagonal heat current, is equal to the steady state work rate that can be obtained within this framework. So in the collisional model, in the repeated collisional model, the interaction with the bath is mimicked by the repeated collision of each degree of freedom in the system with some ancilla. Um, and the fact that you have repeated collision with this ancilla corresponds to terms in the Hamiltonian that you turn on and off, and so this gives time-dependent term in the Hamiltonian that corresponds to a work term. And yeah, well, I make reference. I refer here to two papers. Gabriele has been quite active in this field, and I think on Wednesday morning he will present some new results within the collisional model framework. Uh, well, I haven't told you explicitly, but here I'm assuming that my Hamiltonian is time independent. Otherwise, here I will have an extra term depending arising from the fact that there's yeah, there's a work term. Okay, so well, now I know which heat current enters in the second law of thermodynamics. I would like to use this result to study a model of autonomous device. And so I consider system of rotors with NS levels. So classically, this corresponds to a clock model, and each level corresponds to a specific position of the clock hand. This is the Hamiltonian. So you have an interaction part, and you have a term coupled to a transverse field. And here the operator mu measures the state of the rotor, and the operator sigma rotates the state in the counterclockwise direction. So they correspond to a generalization of the sigma z, sigma x operator.
And you have only about 2 minutes.
Yeah, just very important is this term phi that adds chirality in the interaction Hamiltonian. So yeah, to cut the long story short, if you consider three such rotors, different temperature, T1 is cold, T2 intermediate, T3 is hot, then you see that you can extract heat from the cold reservoir. So K1, 2, K1, 3 are the coupling strength between the different spins. Here, tau, the transverse field is 0. These are chiral term. And you see, so Q dot 1 here is positive for this set of parameters. So this system is working as an absorbing refrigerator, extracting heat from the cold reservoir. You can evaluate the efficiency of this machine, the coefficient of, well, this is the efficiency. And well, you can see also that when you turn on the transverse field, so when you add coherence to your system, the heat, so this light blue curve, the heat that you extract from the cold reservoir decreases and then becomes negative. And so this is a typical example of a quantum machine where quantumness is detrimental for the performance of the machine. So at large tau, the cold reservoir behave as a sink. And yeah, I conclude by saying that I hope I convince you that you can recover the second law thermodynamics for local master equation once you identify the correct term that enters the second law thermodynamics, and that you can use system of rotors to build autonomous thermal devices. Thank you.
Thank you. Thank you very much, Alberto. Thank you. So again, if you have, to the others, if you have any questions, you can either raise your hand or you can post it in the question and answer window. I'm going to wait for the question. Wait, Alberto, maybe can you put this up again? Yeah.
Yep.
While I'm waiting for questions, can I ask you maybe naive question about your two heat currents? I didn't pay close enough attention. Could you tell me whether there's a relationship between your non-diagonal heat and quantum heat of Alexia of Fs? Do you know what I'm asking? So you have this non-diagonal part. Yeah, this one.
Yeah, it's the diagonal can be so the Hamiltonian can be divided into diagonal and non-diagonal parts, and then this is the standard definition of heat current. So H times the dissipator by on rho, and then you just you just split the Hamiltonian into two parts. So you have these two terms, and only this term enters the second law thermodynamic.
Do you know the paper by or the concept of quantum heat that only occurs when you have coherences and you take the system and drop it into a bath? So you basically you lose those coherences to the bath, then you have quantum heat occurring. And I wonder whether this is the same thing as your non-diagonal part here. Is it or is it not?
Well, I don't know
you're not sure.
The paper you're referring to, so maybe you can send it to me. But what I'm sure about is that it's the diagonal part that enters the second law thermodynamics.
Okay. Yes, I agree. Okay. Good. Any other questions? Anyone? Oh, people are a bit lazy.
Yes. So maybe I have one question. Yeah, thank you for this interesting talk. I was just wondering, have you looked at a kind of extension of that when you were maybe about to speak about that when the system is driven?
No, we haven't thought about this, but yeah, there are proofs of the second law thermodynamics when you have only one bath and the system is driven. So it's just a matter of combining those results with ours. Yeah, I'm sure the second law will hold. So it will amount to add, as I said, an extra term here to the energy balance. When you have the Hamiltonian that is explicitly dependent on the time.
Okay. But yeah, what I mean is do you expect also to have this I don't know exactly how to call it, like this kind of duality between diagonal and non-diagonal terms?
No, and well, in the work, so the work is the work, right? So the mechanical work, the one arising from the partial derivative of the Hamiltonian with respect to time is what it is. So that one should enter in your energy balance. So I haven't tried to calculate that, but myself, but I would say no, that there won't be such duality.
Okay, now I mean, yeah, maybe my comment was a bit confused, but it's because yeah, I mean, you can expect maybe in some region that part of the contribution from the external driving might enter maybe into the heat as a contribution to the heat. But maybe it's in maybe more exotic region where you have strong coupling or.
Mhm. Mm.
I must interrupt now because in the interest of time we have to move on. I think these are very interesting discussions, but as far as I understand, this was not covered by this work, but I think